All right, now our speaker today is our own club member, Dave Anderson. Dave is going to talk about he's going to be talking about robot software, which covers a lot of ground. And so he's going to give us some of the insights of his vast knowledge, and hopefully everybody will enjoy it. And please give me a round of applause for Dave.
Our speaker.
Is there a robot back there?
He's practicing for December.
He just does it when he runs into something. Oops.
Or falls over.
I want to thank Doug for encouraging me to do this. For those of you who don't know, Doug Parody is our president, serving his second term, and has done an excellent job.
There is a term limit, so December, I'm out of here, dudes.
And that'll be a sad day. And for those of you who don't know, Steve Edwards, our vice president. Here we go. Richard is our secretary. James is treasurer. And John is our librarian. Did I get everybody? So that's about half the people here, right? Anyway, I've had a lot of input from them. I also want to thank Dave Ackley and Steve Edwards and Ron Grant. Where's Ron? Ron Grant, he's hiding over here. And Mark Sims, who's not a member of the club, but who's given me a whole lot of help and encouragement and feedback on this whole project. And it's real useful to have more than one brain involved. So Inbot was here running around. This is the robot Inbot, which is a two-wheel balancing robot, which I'm going to use for some of the displays today. I'm not really going to talk about the balancing algorithm, which is what most people are interested in, the two-wheel robot. That'll happen on a different day. But what I want to do here initially is, when we think about a robot, normally what you think about is the physical robot. So this is a robot. It's a thing. It has wheels and motors and actuators and so forth. This is a robot. This is a robot. It's something you can see with your eyes. I want you to divide that into two pieces today. And one piece is the physical robot itself, motors, actuators, and so forth. And the other part, according to our little cartoon here, come back, cartoon, is an embedded controller, a microprocessor that controls the robot. So I'm going to briefly go over the hardware here, but we're not really talking about the physical thing you can see today. What we're talking about is the abstract software that runs inside the microprocessor. So, robot, just briefly go over the hardware, and then we won't talk about hardware again. It's got a pair of wheels. Those are driven by a pair of motors under the bottom, the little black columns on the back of those are shaft encoders, so that it can measure the speed and the direction of the motors. On top of that, here in the back, there are a pair of DC-DC converters. One of them generates 5 volts for the electronics, the other one generates 6 volts for the sensors. Here in the middle, you see this little black box is an actual inertial measurement unit that gives me the tilt angle. Over here is an Atmel 2313 microprocessor that does a protocol conversion between that die and the main processor. So this second deck here has the processor on it, and it has some sensors. There are 2 sonar ping sensors, there's 2 infrared sensors, and there's a third one, if you can see it, down here between the front wheels, so it can see when it runs into things. Up here on top, here on the end is an XB wireless connected to the end of, you can't really see it, you can see it from the top. Here's the battery. So the weight of the thing is at the top. This is not a statically balanced robot. That is, it won't balance without the motors running. It falls over. The weight's all at the top, like ours. And that's how it generates its momentum. I've got a little button array here and a knob that I can use to control the robot, and a little LCD interface that's my feedback. So those are specific to this robot, but all of these robots up here have essentially similar design here. This one, pair of motors with encoders on the back. There's a 24-volt battery. There's some DC-DC converters here, and a processor and a motor controller. Oh, I left out one piece. this is a H-bridge, a dual H-bridge, which is what the microprocessor uses to drive the motors. These little flashing guys here are ping sensors, and we can just ignore that. As a matter of fact, I'll turn that off so it's not annoying. So this is the image that I want to talk about today, not really the physical robot itself, but the controller. And for amateur robotics, experimental robotics, the kind of stuff we do in this club, most of us use embedded controllers in one form or another. This is the embedded controller that this robot uses, which is an old Mark Castelluccio made these. It's a 68332. It's called a mini RoboMind. It's getting a little long in the tooth. This was cutting edge technology 20 years ago. It's still one of my favorite robot controllers. It's cutting edge technology 30 years ago. I'm getting a laugh over here from 40 years ago. It's okay, it keeps me honest. It has a whole lot of I/O, and the really nice thing about it is it's got a parallel timer processor, which has 16 timer channels that can do lots of cool things for you. But as I say, this is kind of an older version. This is one Ron will be familiar with. This is an Omega Donkey that he and Mark Sims developed a few years ago. It's an AVR processor. Has this cool touch screen on it. And do y'all even sell these anymore?
Well, we've got about 500 of them left with the
Well, there
touch
you go.
screen, so we need to sell them. We were going to
So,
sell them to Tanner. But
If you need one of these cheap, talk to this man. Here's a fairly common controller. This is a Arduino Omega, what is it, 2560? Got 256K of flash and I think
8K. Right?
full 8K of RAM. So, no, lots. And it's a 16 megahertz processor. It's an 8-bit processor. That's the AVR processor. Here's one, which is one of my current favorites. This is a Teensy. It's an ARM processor, so it's a full 32-bit processor. It's 128K of RAM, 256K of flash, and a 96 megahertz processor, full 32-bit processor. And you know, it just looks like something you dip in chocolate. Bought this across the street at Tanner's. Do you remember? Is it
About 18 bucks.
18 bucks or something like that? So when you consider that this is like, you know, maybe 100 times more powerful than this, and these were about $100 when they were doing
Maybe 10 times.
I have some numbers.
Oh, you did?
I
Oh,
have-
okay.
I have
You have
some- I don't
numbers,
have
okay.
Obviously, this one, you know, the I/O is a little bit limited. You got all those pins, but if you get anything useful, it's going to be kind of hard to work with. Here's a very interesting card from ST Micros. This is the same ARM processor, but they've given you an Arduino I/O as well as their own I/O, and it's a really nice little processor. This is the one I've been looking at.
So does the ARM and the AVR on it?
No, it's just the ARM. This here is a programmer for the ARM. So
And
you
a
can
debugger.
And the debugger. It's pretty cool. You can run the whole thing over serial port. It's powered over USB. And I don't remember how much these cost. Steve, do you?
$10.23.
$10.43. So they cost half as much as one of these?
Yeah.
Well, what kind of sense does that make?
Because we need something tiny, though.
Yeah.
It's handy to have the
Well, I know
It's the same
know.
pricing strategy as women's lingerie.
I'll remember that.
The smaller it gets, the more it costs.
I think, Ray, aren't you using one of these on your LiDAR? Yeah, so there's several people
But yeah,
here.
the convenience of that is if you're doing like a circuit board, it's easier to integrate that in with a small board if you're paying per square inch, which most people do.
Tell you what, if you're troubleshooting, your USB cable is going to knock this thing off the table. I've already seen that. I can't find the, oh, here it is.
Oh.
I'm in the process. When we talk about embedded processors, and you pretty much have a general knowledge of what that means, and that's really what today's talk's about. But there are new things on the horizon. This is a Raspberry Pi 2. This is a BeagleBone Black. And these both run Linux. This one will actually run Windows 10, if you were so inclined. So are these embedded processors? I mean, what does that term really mean? You know, and we'll get back to these later. But so there's some very, very interesting things happening at this level, if you want to pursue that.
It's okay, those TVs up there are running Linux too.
This is our Linux TV man right here. So I think as I say, I was kind of adjusting my talk up and down for the knowledge of the people here, and I don't want to go overboard on things that are well understood. So we'll leap on beyond this. In general, when we talk about the robot being controlled by the microprocessor, what we're saying is that there are a bunch of things down here that are physical, motors, actuators, and so forth. And up here, this guy is going to somehow send commands down here for this to do something. And there are really two large-scale ways to look at that. And the first one we're going to look at is called open-loop control. Open-loop control is when the microprocessor just sends a command to the base, and the base does the command. I'm going to use this little robot here to demonstrate open-loop control. And our demonstration is going to be very simple. We're going to just try to drive a motor. So here's our example. You know, these motors all drive at different voltages. We have 6-volt motors, or 12-volt motors, or 20-volt motors. These are 19.1-volt motors for reasons that are never really understood. So for our purposes, we're going to say when you're going full power, you're going 100%. For one battery, that might be 6 volts, or one motor, it might be 12 volts, but for our purposes, we'll say 100%. 0 is stopped, minus 100% is backwards. So we're going to tell this robot here, I think I can do it on here on the table, to drive its motor forward. Let me be sure I have it set up here. Open loop. That is, we're just going to send a command from the microprocessor to the base and say drive. And there he goes. Well, a couple things you notice. I'm driving it real slow on purpose. And the first one is it's not going in a straight line. And the reason it's not going in a straight line is because the torque of the two motors is not exactly the same, especially when you're going really slowly. Furthermore, if we try to drive over something, and that wheel just comes to a stop. It can't drive over my fingers. So, and this one's not having any trouble, so it's driving fine. If you think, for example, that this robot was driving along and it came to a slope. As it goes up the slope, it's going to slow down because it takes more power to go up the slope. When it gets to the other side, it's going to speed up coming down the slope because you have gravity working with this. By the same token, if we took this out and set it down in the grass, it would drive slower than it drives in here because it takes more friction on the grass. If we put one wheel on the sidewalk and one wheel on the grass, it's not going to go in a straight line. It's going to curve in toward the slower wheel. So, in general, the idea of open loop means that we're going to tell the robot what to do, but we don't really know what it's doing. We just know what we told it. If we close that feedback loop, if we get something back from the robot that says what we're actually doing, that's referred to as closed loop control. And I'm going to turn on, I'm going to close this feedback loop here by telling the robot to read the encoders so that we not only know what we're telling the robot to do, but it's telling us what it does. And the first thing you see is, well, it drives in a straight line now because it's getting feedback from the motors. The second thing we'll notice is that we can drive it hot. We can drive it really slowly. Slower than it would even move if we were open loop. It still goes in a straight line. And if it runs over things, it'll actually ramp up the voltage to climb over them because it knows what the robot is doing. Now, let me stop for a minute. I'm not throwing shade here at open loop. It's the way we all start in robotics. When I build a new robot, it's the first behavior, one of the first behaviors that I get to work. It's always useful to be able to shut off all the other behaviors and get back down to open loop. If you have to replace a motor, some of our teams have had to replace a few motors, or you want to do some other servicing of the robot. It's always useful to get back down to that level. But in terms of controlling the robot at a higher level, open loop, you run into these problems I just described. So anytime we take feedback and we use that in our control, we call that closed loop. I want to be a little more specific about this here. The microprocessor told the base what to do, but now the base is telling the microprocessor what it did. In that way, we've closed the control loop. And our software looks very different. We'll back up to the previous one. For open loop, all we had to do was we said, I want this robot to drive forward at half speed, so I'm going to set motor voltage, whatever that is, to 50%. And I'm done. That's all I had to do. On open loop, we need to read what the robot's doing and use that to determine what we're going to tell it. So our software looks a little different. First thing we want to do is we're going to sense the velocity. And then we're going to generate an error. And that error is, what did we request? Minus what did we read? Let's say once again we requested 50. And let's say that the velocity we read was just 40. So our error will be 10. Instead of writing the motor voltage directly now, we're going to accumulate the motor voltage. We're going to accumulate that error. So we're going to add 10 to whatever this was. And then we're going to delay a little bit to wait for the system to respond. And then we're going to do that again. Eventually, as we do this, our velocity and our requested velocity will match. So we're asking for 50, and we measured 50, and this is 0. So when we increment this, we increment it by 0. We've reached our set point. Now, we hit a slope. The robot starts going up slope, starts slowing down. This number begins to get small. So we begin to increment this again. We hit the other side of the slope. We're speeding up. This number gets larger than this number. Error becomes negative. So we're decreasing this voltage. So when we say open loop, closed loop, the word loop actually has two different meanings. One of the loops is the flow of data, the flow of information. It flows from the microprocessor to the base, it flows from the base to the microprocessor. The other loop, however, is the loop of the control itself. And we're no longer just sending a single command to the base. We're sending a series of commands to the base each time around this loop. I want to talk just a minute about this delay. I was kind of, let's wait for the system to respond. What does this mean exactly? The microprocessor, even when you have a fairly complicated task, robot task, the microprocessor really is going to accomplish that in microseconds. The measurement of how long it takes to do this is in microseconds. But the response time of the robot, the physical robot, the inertia, the mechanical systems and so forth will be measured in milliseconds. So these run very quickly compared to these. So we need to wait for a certain period of time. We'll talk about that for two reasons. And the first is that the system's response has got to be built into the control loop. If you look at this particular algorithm, we were looping around 1,000,000 times a second around that loop. Each time around, we would see essentially the same sense. We said, well, the robot hadn't moved. Let's kick some more into the motor voltage. Long before the robot had a chance to respond. So you have to figure in how much physical inertia and response time the device itself has. Secondly, the sensors take a while to return their data. Sonar sensors, for example, take about 20 milliseconds to give you an accurate readout. Here, since we're reading encoders, we're trying to count encoder ticks. So it depends on how many encoder ticks you have. If you have a lot of encoder ticks, you can sample in a real short time. If you don't have very many encoder ticks, that window needs to be longer. So there's two things you have to chase down in that delay time. One is the response time of the robot. The other is how long does it take your sensors to collect data. That feedback, in this case, is coming from encoders, but it could be coming from an inertial measurement unit, or sometimes the motor controllers themselves can give you feedback about what the motor's doing, and so forth. I think that's all I want to talk about that. I think probably everybody in here understands these concepts anyway. Art works on seismometers. He knows a little bit about active feedback.
Some of the junior robotics teams don't understand on the get-go that you have to have that there needs to be a minimum delay, what you were just talking about. So
Yeah.
it's good to reinforce it.
Thank you. One of the things that will jump out at you here is that in our control loop, the amount of time we spend processing is really infinitesimal compared to the amount of time we spend waiting. And that wait time is really the subject of today's. If we were to graph that, you can see that, we might end up something that looks like this, where the vertical axis just represents when is the task executed, and the horizontal axis is time. So we can see here we executed for a few microseconds, and then we delayed for 20 milliseconds. And then we executed for a few microseconds, and we delayed for another 20 milliseconds. In general, in robotics, the wait time, the time that it takes you to collect data, the time that it takes the robot to respond is large compared to what you want to do on the microprocessor, even for pretty complicated microprocessors. So keep this chart in mind. We're going to come back to this in a moment. I think that's enough.
You got a question?
For your delay, is it, for most of the motors that you've used, is 20 milliseconds?
This guy, his top level loop runs at 50 hertz, so that's 20 milliseconds. This guy's top level loop runs at 25 hertz, so that's 40 milliseconds. The biggest difference there is it takes the IMU a little while, and I don't have very sensitive shaft encoders. Here, I get, I don't know, I think I get 1024 ticks per revolution per motor. So I've got thousands of ticks to work with, and therefore I can use a shorter sample. Right. My first robot ran at 10 hertz because I had read that the space shuttle ran at 10 hertz, and I thought, well, good enough for the space shuttle. That's good enough. Good enough for me.
You might even get more on that robot, David. What's the gear reduction on those motors? Is it like 20 to 1?
No, it's
Not so much. 5?
no, it's like 60 to 1.
Oh, 60 to 1.
Yeah.
Are those 500 count per rev?
They're 1024
1024 count per revolution of the motor?
of the motor. Plus,
Okay, then you
I
get
get a
your
tick on both the rising edge and the falling edge.
Okay.
Of those, so I actually get 2048 ticks per revolution of motor.
Of the motor.
More ticks, I mean, that's way more than you need,
Right,
but
right,
it's
right.
better to have too many than not enough. You can't do math on just 5 ticks, you know. You can't really control the thing very well.
So, but with that gear reduction ratio, then you're talking tens of thousands of ticks per inch, probably.
I actually have a number
Okay.
here that I can
Okay.
pull out. We can look it up.
Okay. Anyway.
So, all right, with that in mind, I would like to introduce Steve Edwards' generalized control loop, which is we're gonna write all this code in C. And in C, a while one loop means do whatever is between the curly brackets forever. We're never gonna exit this loop. And Steve says the basic generic control loop is sense, think, and act, and then delay. You find these loops all over the robot. I will just pause and say editorially that there was times in my foolish youth that I wished I had followed this sequence. Sometimes they gravel. These kind of loops run all over each one. They run at low levels, they run at high levels, and the construction of an infinite loop is not something that you really see a whole lot in normal software when you just sit down and code. But it's something we use all the time in embedded robotics. As a matter of fact, it's pretty much all we use. Pretty much the basis of all the software you write are these endless loops. And as I say, they exist at all levels. So let us. I'll jump over
Dave,
part
I
of
was
that.
gonna say, even if you're using a sophisticated real-time operating system, the tasks themselves all have little endless loops in them too.
Yes.
So
Yeah.
it can be as simple as that's the whole robot software is one loop, or you can have multiple.
You have lots of loops. And in point of fact, that's what we have. There's, as I say, there's levels like robots like this. So let's look at some of those levels. I must have skipped over a page here. Okay. Here's an example of one that's actually running on InBot. This is a low-level loop that reads the A to D converter. So can you see my mouse here? Yeah. Okay. So there is a subroutine that's called sample ADC. I've got a pipeline A to D converter with its 8 channels. You call that subroutine, it reads those 8 channels and puts them in an array. And then I've got a user vector here. If there's something in that vector, if there's a function pointer in that vector, it'll execute it. And typically what I do with that is I low-pass filter the A to D converter because A to D converters are generally noisy. And then we call a delay down here, which I've just written very generically as delay. And I think on this robot that this actually runs at 100 hertz. So that delay would be 10 milliseconds. So every 10 milliseconds, we read that low-pass filter, stick it into an array where other tasks can get to it. Next is what I would call a mid-level infinite loop. In this case, we're going to read these sonar units here. And I have 2 variables here, define left ping and right ping, which are global variables, which is how the rest of the software will interact with this. So we sit in an endless loop here, a while one loop, and we ping one of the sonars. So there's a subroutine to ping the sonar. And then we wait a little bit, 20 milliseconds, and then we read the result of that ping. And those get written to 2 variables, left and right ping. So any other task that's running on the robot just reads those variables. They don't have to know that there's actually something fairly complicated going on here, which is that we're setting up a timer, and we're initiating a pulse, and we're listening for that pulse to come back, and we stop the timer, and then we convert that into inches, actually in this case, tenths of an inches, and so forth. The other tasks don't know that. All they know is there's this thing called left ping, and when I read it, I know what the left ping value is. And in general, that's the way all of these work. I was looking for a good example of a high-level infinite loop, and I couldn't really find an easy one. So this is the one that actually balances the robot, and it's kind of hard to follow what it's doing. But it runs at 25 hertz. And we're going to define this thing called key size, which we're going to get back to in a minute, which is the size of your timer. And we're going to set it to whatever a current sys clock is. And then we're going to sit here in this infinite loop. And the key piece of information here is at the bottom of this loop. There's this thing called period, which is going to give us an exact, precise timing of this event. So in this particular one, all it does is sets up the speedometers, and then it calls this command motor command. Motor command reads all of the sensors and balances the robot. That's all you get to know about it in today's lecture. We'll cover it in another lecture. So, okay, so essentially that balances and drives the robot. The point I'm making here is that there's not just one of these big control loops, there's lots of them, and they're running at all different levels of the robot. So it'll be useful, and talk a little bit. We say, well, what we're talking about is concurrent loops. That is, it looks like these loops are all running simultaneously, but of course they're not. The processor can't really do that. So how do we implement what I've drawn here in the cartoon? We've got loop 1, loop 2, loop 3, and loop n, and they all appear to be running at the same time. How can we actually implement that in practice? There's 3 different ways I want to talk about. The first way is we do it with interrupts and timers. We'll do it with hardware. The second way we do it is with augmented finite state machines, which is a very common way to do it in robotics. And the third way is to do it, as Richard said, with multitasking. We actually can do this with multitasking. So let's look at some examples of each one of those. You guys stop me. I mean, we have a small enough group here. If you have questions, if I'm jumping ahead too quickly. We good? All right.
One question.
Sir.
Would you mind moving your robot?
Well, Steve said there would be only one chair where that was in the way.
And I think he's in it.
And it's the chair.
You picked it.
There we go. Nope.
Could you please move your back?
There we go. How's that? Okay. Let's see if can I zoom this a little bit? Okay, when we try to do concurrent loops with interrupts and timers, which is a very common way to do it, and I want to emphasize here, these are not either ors. These are not 3 different ways that you have to choose among. And on these robots, all 3 of these are running. So with the concurrent loops with timers, the first, I've got 3 points here. And the first is that the tasks are generated as interrupts rather than subroutines. That is, you have to tell the compiler this is an interrupt. And it builds it slightly differently. The way interrupts are called and the way they return is slightly different than subroutines, so you have to let the compiler know. The interrupts themselves are generated by hardware timers. That is, something built into the microprocessor that runs a timer that can count down and generate an interrupt. And the tasks themselves are not loops. They're loops in our head. They're conceptually loops. But where we actually implement them, they're not actually implemented as loops. So we'll look at our example here. We want to run a 1 kilohertz sys clock, like we looked at in the previous example. So we want some variable in memory that changes its state every millisecond, and it's a counter. So conceptually, we're in a little tight loop where we say infinite loop, increment the sys clock by 1, and then delay for 1 millisecond, and then do that again. So that gives us this running clock. Now, to actually do that, is that big enough to see? We're going to define an unsigned long and call it sys clock. I said we'd talk about this a little bit. This is a good time to do so. 1 millisecond timer is going to overflow after a certain period of time. So if that timer is an unsigned long, that's a 32-bit timer. So that means that that timer will overflow when we've used all 32 bits. And at a rate of 1 millisecond, it'll overflow in about 49 days. So for this timer, the universe ends in 49 days. Now for our robots, that doesn't make much difference. A really long run for this robot might be 4 or 5 hours. That would be really long. 49 days, I'm very comfortable with. But if you were going to use a system like this to do something like control a hydroponic garden or something like that, you don't want to go out and reset the thing in the backyard every 49 days. That would be a total pain. So we might want to define that sysclock as a larger number. Next step up, we could define it as a long, 64 bits. Unsigned long, running at 1 millisecond, will overflow about every 200 million years. That's probably okay. You probably go out and reset your garden every 200 million years. It'd probably be all right. So this is a decision you have to make when you build a system like this in terms of how you're going to use it. 16 bits is too short. It overflows in just an hour or something like that. So 32 bits is a good handy number, and a lot of processors, it's their basic integer. It's a 32-bit integer. So that makes it very easy to use. Okay, when we build the interrupt, we have to do two things generally. And the first one is we're going to tell the operating system, the compiler, that it's an interrupt. That's what this attribute interrupt thing here, that's an instruction to the compiler. It says don't make a subroutine out of this, make an interrupt. And then all we're going to do is we're going to increment the sysclock by 1. This is a pretty simple interrupt. So that's step 1. Step 2 is you've got to set up the timer. And that also usually requires 2 steps. I've generalized them here to make them easy. Ron actually found, was it the Teensy 3.0 library, where you set up the timer. It looks just like this. It was great. I mean, it was real simple. So we have 2 steps. The first one is we have to tell the microprocessor what subroutine to run when this interrupt occurs. And that's what this first line does. I have a routine called interrupt catch that I run, and I tell it I want the interrupt to catch whenever timer 1 interrupts, and I want it to run sysclock handler, which is this thing we just defined up here. So that's step 1. Step 2 is then you have to initialize the timer. And this is very hardware dependent. I've just said here that I want to initialize timer 1 to run every 100 microseconds. Every 1,000 microseconds. Thank you. So what's going to happen is when this is set up and this initialized sysclock is executed, which will be sometime during your initialization code, is this timer will begin, come in! Come eat pizza! Oh.
This is for a virus group.
Oh, okay. Yes. We can't have. So the way you think about this is that this code is running in the background. And that's the term we use, the background. This timer is going to set itself up for 1,000 microseconds, and then it's going to count down. And when it hits 0, it'll generate an interrupt. When it generates that interrupt, the CPU will say, what am I supposed to do when this interrupt runs? I'm supposed to run this sysclock handler. And so from the point of view of any task running in the foreground, it doesn't really know that once every millisecond, this task is taking a few clock cycles and CPU cycles and using them to increment that timer. The timer, from the point of view of the foreground task, just seems to magically change. All we know is that when I read sysclock, its value will be different. So for example, a foreground task might say, well, I know how long an event took, so I'm going to read and copy that sysclock. And when the event's over, I'll read it again, and the difference between them is how many milliseconds passed. So in this way, we have a way of keeping track of real time. The number of tasks you can run like this is, of course, limited by the number of timers you have. On this guy, I've got 16. I think the AVR and the ARM both have 3. There are some nifty libraries out there. Dave Ackley pointed me to one that allow you to use more tasks than just the 3 hardware timers. But essentially, they work the same way, which is that you set up an interrupt and you say how often you want it to run. And that code doesn't run at all until the interrupt happens. And then it happens once. Yes, Dave?
One of the things, so if you're doing C, typically you use the term volatile on those. Keep your compiler
Keep the compiler happy. Yeah. And if you're doing it, well, we'll get into that in a minute. So, as I say, this is not an either or. All these systems are running on these robots. So this is one level, and this is one way you can make tasks run concurrently, is by doing it with hardware interrupts. And there are some fairly sophisticated ways of doing this. The AVR doesn't really have a fancy interrupt processor, but the ARM and the 68332 do. You can have multiple levels of interrupts. They can interrupt each other. You have priorities, and It can real quickly get out of hand. But you can do some quite sophisticated stuff. So that's our first way of making concurrent tasks run. The second way is to do it, as I mentioned before, with finite state machines. And what we're going to do with finite state machines is that there'll just be one great big loop, and it calls each one of these tasks in turn. The tasks themselves are responsible for keeping track of their state. So this is not like the interrupt, where the interrupt tells you when to run, and you just run when the interrupt happens, and in between you're not doing anything. In this case, you're always running. You have to keep track yourself of whether you're supposed to execute. So the tasks themselves, again, are not loops. So here's our example. We want to flash an LED at 1 hertz. So conceptually, we're going to say, I want to wait 500 milliseconds. Then I want to turn an LED on. Then I want to wait another 500 milliseconds, and I want to turn that LED back off. And we're going to sit in an endless loop. So we have this LED flashing on and off once per second. This one looks very different conceptually from what we actually end up coding. So for the finite state machine, we're going to define 2 variables. And the first one's called state, which will keep track of our state. And the second one's called wake up, which we'll use to know when we're supposed to execute. And we have 2 states here. So when we first entered this program, the first time, because we haven't initialized them, state and wake up will both be 0. So we say if state is equal to 0, and it is, then if wake up is less than sysclock, and it is, because it's 0, whatever sysclock is, then we're going to turn the LED on, and then we're going to set our wake up time equal to whatever the current sysclock is, that sysclock that we just set up with an interrupt in the last example. And we're going to add 500 to that, and then we change this and set the state equal 1, and then we'll exit. The next time around this big loop, and let's jump over here and just to get you for what I mean, the control loop is going to look something like this, where we have a big control loop, and somewhere down inside of it, we're calling this flash LED, and it runs continuously. It's the loop that runs continuously. So the second time around this loop, we'll enter this, and state is no longer 0, state is now 1. And we'll say, well, is the wake-up time less than the sysclock? Well, it's probably not, because we set the wake-up time to 500 milliseconds in the future. So we'll just exit that, and that'll happen each time around the loop for 500 milliseconds. We may be going around that loop, at a megahertz. On the ARM processor, we almost certainly are going around the loop that fast. So we might have to wait a long time. There are many, many, many trips around the loop before we're ready to go into the next state. But eventually, the sysclock timer becomes greater than our wake-up time. So our timeout has expired, greater than or equal to. We'll turn the LED off. We reset our wake-up time to whatever the current sysclock is, plus 500, and we set the state back to 0. Next time this comes through, the state will be 0, but the clock won't have expired, and so we go back into this process. Well, again, we'll have a whole bunch of tasks running concurrently here, but each task is running every time around the loop. And the task itself is deciding whether or not to execute or wait or whatever. In a real set of finite state machines, you often have more than just 2 states. So this is a very simple example. You might have many states. And if you have many states, it becomes kind of clumsy to code it the way I wrote it here. You would probably do it, you might do it with a switch statement for those of you who know C. But I would be more likely to do it with a function vector. So like we looked at for the low-pass filter. So we'll jump over here and look at what that might look like. In this case, we also have state and wake-up, but state is now defined that it contains a pointer to a function. And we initialize it to point to the function LED1. So now our flash LED is very simple. We just jump through that vector. That's it. So this is the whole command here as far as the loop is concerned. And then that vector can have one of 2 states. So they're now defined as little subroutines. And they do essentially the same thing. The difference is, if we go back to the previous version, this decision actually has to be made twice. In embedded processors, we're always trying to get things to be small and run fast. So as a general principle, the decision was made once here. We said, wake up is less than sysclock. So we should set the state equal to 1. The decision is made. But the next time through the loop, we still got to test it again. What is the state? Oh yeah, the state is 1. we have to test the state a second time, even though we already made that decision. If we jump through a vector, we only test it once. So each, the wrong way. So each time around this loop, we just jump directly through the state vector. And down here, instead of setting the state to 0 or 1, it's a vector and it points to that subroutine. So each time through the loop, we jump directly to it. We don't have to make the decision. That doesn't make much difference here. It's about the same amount of code. It looks about the same. You get to something that has 5 or 6 or a dozen states, it really makes it much easier, faster to run. You're not having to test 9 states and say, no, it's not that one, it's the 10th one. You just jump directly to the 10th one. So that's a little easier way to write it. And some of the code that runs on here is actually written in that way. I think that's all. Any questions about finite state machines? I call these augmented finite state machines because in the purest sense, they're using a timer to change their state. And in the purest sense, a finite state machine would only use its state and its inputs to choose its next state, where we have something internal going on here, which is a timer. So they use the term augmented. That just means a finite state machine with a timer. The third way we can do our concurrent loops is with multitasking. And I'll talk about this just a minute. There's lots and lots of options available here. There's lots of free options available. There's lots of commercial options available. Every chip manufacturer will have some kind of multitasking schedule or something like that. Every board manufacturer has it. There's a really, really nice one that's, that you can get for these little cards from S.G. Thompson, I think it's called. It's CMIS. Anybody here know? CS?
CMSIS.
CMSIS, thank you.
Pronounced Simsys.
Simsys,
Oh,
all right. And there are some very expensive commercial ones that do lots of stuff. There are some free ones that are quite sophisticated. We set up some of those this summer and worked with them. So there are lots of different ways to do that. The examples I'm going to use are from the one I use, which is a lightweight multitasking scheduler. It's just a few hundred lines of code that runs on all my robots, the big ones, the little ones, even the little Lego bot. So let's take again our analogy. Conceptually, we're going to flash an LED. In this case, we're going to turn it on, wait, turn it off, and wait. So it flashes once a second. And then if we look at the code, one of the things that will jump right out at you is it looks just like the conceptual. And point of fact, that's one of the huge advantages, that what you're coding is very, very much like the way you conceptualize it. There again, be 2 states like there was in the previous one. I'm sorry, 2 steps. And the first one is that we define the code, and the second one is we'll have to start it up like we started up the interrupts. The key here, the key thing to focus on is what happens during this delay. We saw in our previous graph that our execution time is microseconds and our delay time is milliseconds. So what happens during those millisecond delay? In a multitasking system, what happens is the other tasks run. That's when they run. It's when you're waiting. And in point of fact, even when they're all running, there's still a lot of waiting going on because of the need, the necessity of incorporating the time constants of the robot itself. So I keep saying that these things are running at all different robot levels. And I'd like to take a minute and describe what I mean when I use that term levels. I say it's running at all different levels of the robot. What are the levels of the robot? We've already talked about level 1, which is essentially the physical robot itself. And we've talked briefly about some of the things that are running in that microprocessor. Well, we'll start here. I want to add a level below the robot, which is level 0. Level 0 is the world. And the reason that that's in there is because it's the world that closes your feedback loops. When you have closed loop control, it is the world that is feeding back the information to you. So for example, if you have a robot that takes some readings, based on those readings it moves, and then it takes more readings. The position that it moved to is controlled by the readings that it took. So the new readings that it takes will be controlled by the position that it's in. So there is a feedback between the readings and the robot's position. And there's a feedback between the robot's position and the readings. Therefore, and interestingly, as you close that loop, the world itself is a very, very important part of that feedback loop. And there's not really any way to simulate it or to predict it. You have to test it. You have to set the robot down and let it run around and see how it interacts. And all kinds of behaviors will emerge that you didn't program and that it never occurred to you might be there. They're called emergent behaviors. And they have to do with the way the system is interacting with the world. I have a simple example of this. If you imagine that you had a long wall and you had a bright light source behind. So the robot is doing two things. It's trying to get to that light source. It's seeking on a bright light, but it's also trying to avoid obstacles. Well, let's say this is a couch here in the way. So the robot's headed toward that light, but he sees the couch, and he can't go toward the light. So he turns away from the couch. Well, now he can't see the couch anymore, so he can turn back to the light. And now he sees the couch again. The result is that the robot swims along the perimeter of the couch, turns around and goes to the light. Well, you never gave it a couch perimeter following algorithm. Nonetheless, that emerged from its behavior because the world is a very, very important piece of the feedback loop. So sometimes that's not obvious. And I know a lot of people will write a piece of code and they set the robot down on the floor. It doesn't behave at all the way they expect it to because they did not take into account that the world itself is an integral part of their feedback loop. So level 1 is the physical robot, which we've already talked about. Level 2 is what I call the interface level. And the interface level is the part of the microprocessor that actually talks to the hardware. One of the things about the interface level is that between it and the robot, I tried to draw here, there are lots of connections. So if we look inside this robot here, if you can see down, that's what this whole row of wires, there's about 40 little wires in there. Those are the connections between the interface level and the physical robot. Let's see if we see it better on another one. No, we can't. It's essentially these. This is the physical connections. And the connections between the interface level and the rest of the robot are relatively simple compared to those. I call this the interrupt level because almost everything running at that level on my robots runs under interrupts, runs under timers and interrupts. So an example might be that we have a timer generating a pulse wave, and that's used to control the motors. We might have another interrupt that's measuring return times for sonar. We might have another one that was the encoder ticks, it's counting encoder ticks coming off the motors and so forth. In general, not totally, but in general, the way those work is that they are doing some sort of complicated driver interface. But the level above them to the rest of the robot just looks like a global variable. So we already used the example of the ping. Another example might be the motor speed, where you just write to a variable, the motor voltage that we saw here. And there's a bunch of stuff going on down there at that low level that we don't care about. We're running at a level above that. There also, I want to just mention in passing, and Dave actually told me I should, that another way to communicate between the lower levels and the upper levels, rather than just with global variables, is to use message queues. We're not going to talk about message queues today, but there are ways that you can decouple the synchronization between the tasks. That it's a refinement. So, and those are also global. So from the point of view of any task running in the foreground, there's some values I can write, and they change what the robot does. And there are other values that I can read back, and they tell me what the robot's doing. And all the rest of that is handled down at that interrupt level. See if there's anything else I wanted to say about that. No, I think that's it. Okay, the level running above the interrupt level on these is my lightweight multitasking executive, and it's the thing that allows multiple tasks to run simultaneously, concurrently, and that's really what I'm going to talk about today, or what I'm going to talk about for the rest of the day. And it is, of the groups that we looked at previously, it is only one of those that is running. That is to say, we actually do have concurrent tasks running down at the interface level using timers and interrupts. And we actually have, in another part of the robot, there are things running using finite state machines. But everything that is running above this lightweight multitasker runs on it. So they're all tasks that are running conceptually concurrently. And that's the way I'm going to describe them, even though that's not really what they're doing. So when I say everything running above that, I've got all these blocked together. But these are all tasks that are running simultaneously, so they really should be side by side rather than from top to bottom. You ignore that. The first group I call sensor tasks, and that's like what we already saw with the ping sensor, where there's a low-level piece of code that knows how to actually run one ping, and then there's a high-level piece of code that knows how to run an array of ping sensors. Another example might be at the interface level, we have accounts that tell us what our wheel encoders are doing. And up here at the sensor task level, we're running odometry. So it takes those things and it tells us not just what the wheels are doing, but what's the location of the robot, what's its pose, what's its vector, and what's its velocity. Get all that information back from the raw information being collected at the lowest level, at the interface level. And once again, that information is made available to other tasks running as global variables. The next block there is, I just said behaviors, that's the subsumption engine. Subsumption is going to be the topic of another talk. And but those of you who saw the talk I did here a few years ago, I talked about it briefly. Richard?
I was just gonna say, you already have a video that covers that a little bit.
Yeah, that covers it a little bit. Essentially, it's all the behaviors. It's a hierarchical arrangement of the sensors and the behaviors on the robot. And we'll jump over that right now, other than to say that at the subsumption level, there's just 2 or 3 tasks running. They are big loops. They all call finite state machines. Finite state machines turn out to be a real handy way to code subsumption, pretty much because each task runs every time around the loop. There's generally no delaying, and it's just an easy way to. The top level there I call the advisors or the supervisors. Things running at this level, again, they're just tasks running. What separates them is that they have the ability to reconfigure the subsumption engine, to reconfigure what its goals are, what it's trying to do. And they do so by monitoring it. A good example of that might be that the subsumption engine can be configured to seek toward a goal and to avoid obstacles in between as it seeks toward that goal. A higher level supervisor might watch to see, well, you've arrived at the goal, so I'm either going to shut off the navigation or I'm going to give you a new goal. That would be running at the supervisor level. Another example might be, sometimes when you're navigating, you can get caught in a cul-de-sac. It's like the robot equivalent of a minnow trap. Robot drives into it and he can't find his way back out. There is a supervisor that looks for that, and if it sees it, it reconfigures the subsumption engine to do wall following rather than navigation. And inside the cul-de-sac, wall following will find the opening and get you out. And once it's out of the cul-de-sac, it switches back to navigation. So things that are running up at this level are responsible essentially for reconfiguring what's going on at the lowest level. I can back up just a minute. If you think about a biological analogy for what I've just described, so you have the machine itself, and then you have a level above that, the interfaces. That's kind of like your central nervous system. It's a creature's central nervous system. And the multitasking is the organization of the signals in that central nervous system. If you think about the subsumption engine, that's like our reflexes. Where you've gotten up to the level, that's what maintains your balance and your posture. It provides locomotion, keeps you from running into things when you're moving, and so forth. And the advisors, maybe we're up to the brainstem. I doubt it, but we're probably still at the ganglia, but it's a level above that. So the 7th level, as you might have guessed, and I've got it in dotted lines, is the brain. And the reason I put that inside dotted lines is because we don't have that part. We don't have C3PO. We don't have your plastic pal that's fun to be with. Actually, we might, now that I think of it. I know sometimes that people who are newly enthusiastic about the field of robotics are often, this man's smiling at me, he knows what I'm going to say, are often excited about the things that they're going to do at level 7 and become discouraged and quit when they find out how far away we are from level 7. But there are lots and lots of things to be done, exciting things to be done. And I will stop and evangelize here for a minute. I firmly believe that where we are in robotics is sort of like where flight was 100 years ago, where guys in big laboratories with lots of government funding don't really have an advantage over 2 bicycle builders in their garage. Nobody knows where we're going. Nobody knows what the result is going to look like. So nobody really has an advantage over the people in this very room. And the way things happen for the next 100 years may well be decided by the decisions and the work that we're doing right now. So don't be discouraged that we don't have a brain yet. There's lots of work to be done, and it's pretty exciting work. And it may well set the stage for a long time to come. So at that point in my notes, it says stop and eat pizza. I guess we're not going to do that part. Well, let's see. How long have I been going? I actually need to pee. So
Well, I guess that counts as not. Oh, no, just,
we got that on video, right?
Yeah, we'll take a bio break.
Okay, let's take a short break. Okay.